Thanks, Artie. Excited to be here this morning with all of you. So I think it's helpful to understand a little bit about me to understand why I care so much about explainable AI and ML. I started my career in product management working on algorithms for genomic and health-related data, trying to predict which types of genomic sequences might be disease-causing. I then started a company that was building algorithms to help understand which job applicants would be good hires. And for the past 4 years, I've worked on algorithms to help buy and sell homes. And I'd say one unifying theme for all of these is the relatively high stakes types of predictions: people's health, their livelihoods, their homes. And when the stakes are high, explainability really matters. I'm going to share a lot of examples from my company, Opendoor. And so I think it's also helpful to understand a little bit about what our company does. We provide a simple, certain, and convenient way to sell your home. You can go to our website, type in your address, and we'll make a competitive offer to buy your home in just a few minutes. What's going on the back end there, and this is where my team really comes in, is the way we make you an instant offer is we actually buy your home. We take that risk, and we do that using algorithms. And so when our ML products predict a price that's too high, those are millions of dollars in losses that can be incurred to us. And when we make predictions that are too low, that's incredibly frustrating, sometimes infuriating to our customers. People care a lot about their homes. All of that has put a heavy emphasis on explainability at Opendoor. So today we'll talk about the benefits of explainability. We'll talk about a couple different frameworks for what does explainability mean. And then we'll spend most of our time on what are some tools to actually produce explainability. And I'll end with some thoughts on the future of explainability. I'd be remiss if I didn't talk about how generative models are changing what explainability means. I won't get too deep into any technical details. I won't talk about any specific vendors. I will talk a little bit about some principles that I think are helpful in terms of build versus buy decisions. So why explainability? Well, first and foremost, user trust. Explainability is often a necessary but insufficient condition for users to trust an algorithm. A lot of the time, users want to understand what went into this prediction, and then maybe they'll give you more information. So most of us, kind of regardless of the field we're working in, the more we understand about our users, the better we can serve them through ML. And sharing something about our ML and how that was formed is often a really key way in getting them to share more back with us. The second major benefit is routing. So one very simple type of explainability, and I'll talk more about this in a little bit, is simply what's our confidence in a prediction? And again, a general principle that'll hold across a lot of domains is we want users or the business to rely more on high confident predictions than low confident predictions. That's the most basic type of routing that there is. Third, fairness. In a lot of industries, there's going to be a regulatory aspect of being able to explain our models. I work in financial services. For a lot of financial services companies, we have to actually share our models and explain them with enforcement agencies. Even if you don't, it's generally the right thing to do to have some level of interpretability of your models to make sure they're not discriminating unwittingly against some type of user. And then last, but certainly not least, is improvement. I'll talk a lot about this, but explainability is key to actually understanding specific predictions, where we might all be able to agree, hey, this prediction was off, and then we can dig in, understand why, and collaborate between an operations team, a technical team, and even end users to drive model improvement. So I've mentioned a couple different types of users who benefit from an explainability. And it's worth being explicit that lots of different types of users will benefit. So external users benefit because they understand the context of a prediction and how much they should rely on it. They also benefit because they understand when they should share more information with you. If they see, oh, there's something I think is really important, and your model hasn't included that, and there's an option to share that piece of information with you, explainability will incentivize them to do so. For internal users, if you've got some kind of human-in-the-loop system, you're using ML in conjunction with domain experts, explainability is important for overrides, or as I think about it, to avoid double counting. Human experts might be really focused on making sure a certain input is included, and they'll want to know, did the model already factor that in? If it didn't, they're going to adjust for that as they should. But if it did, you don't want them to double adjust. It also helps them collaborate with more technical teams to frame their feedback in a way that is going to make sense to the technical team because they understand something about the prediction generation process. And finally, for the technical members, researchers and ML engineers, I think explainability is key for hypothesis generation. I think our best hypotheses often come from investigating specific examples where the model did something unexpected. And explainability also helps determine, what does unexpected even mean? Is this a probabilistic miss that's going to be expected with any model? Or is this something that kind of feels more like a classical software bug? All right, let's get into our first real estate example. And I'll use this example where we've got two homes, home A and home B, where our model is predicting both of them are $300,000 to illustrate a couple different kind of increasingly more sophisticated types of explainability. So the first level of explainability is simply showing what are the model's inputs. So if home A is a 4-bed, 3-bathroom, 2,000 square foot house, and home B, all that we know about it is that it has 4 bedrooms and the other fields are null, we can immediately start to get some intuition around, well, how might we want to treat these predictions differently? They have the same numeric output, but for business use cases, we would probably say we rely more on home A. That takes us to the second level of explainability, which is confidence intervals. So we would expect that given more null information for home B, there should be a wider confidence interval around that numeric prediction. And most model types are able to produce something that looks like a confidence interval pretty much out of the box. The last level of explanation, this tends to be what a lot of us jump to when we think about explainability, and that's causality. That's how are the inputs actually transformed into outputs. The key takeaway that I'd like to leave all of you with when it comes to this framework is that a lot of the time we can get a lot of value from doing the simpler things, just showing the inputs, showing the confidence intervals, before we cross that bridge into what is a harder area, which is actually explaining causality. That said, I'm going to spend most of the rest of my time talking about causality and going deeper there. So the first way that I think about causality is global versus local. So global causality or global interpretability means providing a holistic view of how inputs are transformed into outputs across the entire space of eligible inputs. I think a really simple visualization of this is a decision tree. And so you can take any kind of observation, start at the root of the decision tree, and it'll flow through, and you can visualize all that really easily if you just have one decision tree of limited depth. Most of us don't have models that are one decision tree of limited depth. This is an example of predicting housing values using a gradient boosting model. So we can no longer rely on just looking at the decision tree. Instead, this is showing something called partial dependence plots, which take different features and plot the relationship between that feature and the house price. That last chart on the bottom right that has all the colors is actually showing how two different features interact with price. If you're kind of confused here, that's kind of the point, which is that for real world models, getting a global view of interpretability gets increasingly difficult. And this is not a particularly complicated model. This is actually just a bunch of decision trees all ensembled together. This is way less complex than, say, a foundation model that has millions or billions of parameters. not only is global interpretability, does it get really complex quickly, I would argue it also tends to be much less useful in industry than local interpretability. What I mean by local interpretability is the ability to take a single observation, a single set of inputs, and understand how those are transformed into a single output. So what this looks like for housing is if I want to make a prediction for 123 Main Street, that blue dot, the way that I want to understand it is what were the comparable sales that inform our model's view of 123 Main Street? What are their attributes? And do they drive our prediction up or down? That's the way that most buyers and sellers and agents actually come to a price they're willing to pay or a price they're willing to accept. So if we go down into local interpretability, I'll talk about two post hoc explainability layers that can be applied to pretty much any type of model. The first is called LIME, or Local Interpretable Model Agnostic Explanations. And the idea behind LIME is you kind of treat your model as a black box. You don't even necessarily try to understand the internals of it. You take that model, you make a lot of predictions. You cover your eligible prediction space, and then you take a model that you think is interpretable, so say like ordinary least squares regression, and you fit that highly locally to a particular explanation you want to explain. And then you get the benefits of, say, ordinary regression in terms of linear coefficients. Another fairly common approach is SHAP values. SHAP values, I think, has the advantage of you don't have quite as many choices that you need to make as a developer as Lime. You don't have to pick an interpretability model. There's some fewer output format options, but the output here is pretty similar to if you do Lime with a linear regression. So the top chart here is basically showing, again, this is house price prediction. For a particular house, what are all the factors and what's the sign and magnitude of each of those factors influence on the house price? And then the bottom chart is actually kind of rolling that up into a semi-global view where each point is a particular house price that was predicted, and it's showing how each factor contributed to those house price predictions. But if we go back to the Opendoor example that I showed about house pricing, this actually isn't all that helpful. We don't tend to think about house pricing as a simple linear regression. I'm curious, by show of hands, how many of you have actually bought or sold a house in the past? Okay, great. And how many of you, when you were thinking about how much you would be willing to pay for that house, looked at similar homes in the neighborhood and what they sold for and kind of thought about how similar are they? Are they better or worse? Another quick show of hands. Okay, basically just as many people did that. This is the way that people actually derive and produce or generate prices in the real world. They choose comparable sales. They adjust those comp sales prices, maybe mentally or even unconsciously. They say, oh yeah, that house down the block sold for $500K, but it has a pool, and the house I'm considering doesn't have a pool. So yeah, maybe mine is, this house is going to be worth $450. And then they take some kind of weighted average of those comp sales. And so what we've done at Opendoor to promote interpretability in what we consider a very high stakes environment is that we've built our models to follow this process. So we actually take those comps, we adjust those comp sales prices. And so this is what it looks like for our internal operations team on the back end, where you can see this really detailed view of, for each comparable sale, how does it differ from the home that we are trying to value along all of the attributes? And then ultimately we project all of this into dollar space. And for each of these three steps, we're able to use very sophisticated, large neural networks. But we're also able to then expose interpretability at each step in a way that makes sense to local domain experts and ultimately to our end users. I've talked a lot about structured data, so I'm gonna talk a little bit about explainability for unstructured data. For images, Saliency maps are something that we use quite heavily at Opendoor. I'm actually showing a medical example because I thought it was easier to understand here. But this form of interpretability highlights the pixels that a model is paying the most attention to. And for supervised problems where you want that model to focus on a particular part of the image, it becomes pretty easy to see if the model is paying attention to the right thing. Time series models are another very common model type at Opendoor. For any of you who are doing any type of economic modeling or financial modeling, the vast majority of that will have a time series component. For all of our time series modeling, we're going to break apart our predictions into a trend or a long-term slope, often something that's determined by demographic changes, seasonality, which is the repeating part, and it can have multiple repeating cycles. You could have an hourly cycle, a daily cycle, a weekly cycle, or an annual cycle. It's not an either or. You can have all of those occurring at the same time. And then last, you have a residual. And once you've taken out the seasonality and the trend, you can start to say, do I have a good residual? A good residual is something that should be relatively unbiased around 0, and it shouldn't be repeating. So you can see here in our residual, first of all, it's pretty clearly repeating, and that would tell us that we haven't done a very good job of actually fitting our model. We're not picking up enough of the seasonality. The second thing we would notice from the residual is, hey, it's a lot closer to 0 in the middle of the training period than at the end. We're not in 1961, but the point here would be what you care about in terms of prediction for a time series model is always the most recent part. And so if your model is worse at the leading edge of it, the most recent part, then it's not going to be as good in production as it is over the entirety of your training period. Last is text and generative models. So one of the most fascinating things about these models is that they're increasingly able to explain themselves. So we can start by asking a model, this is GPT-3, who won World War II, and it'll give us a pretty factual answer. We can do something very unsophisticated, simply asking why, and it will start to answer us. We can still be pretty unsophisticated and just kind of tell it how long or how in-depth do we want its answer to be, and it'll comply with that. Citations are something that I'm starting to see become increasingly common for a lot of these models, especially models that are using a specific corpus of information, using embeddings, being able to actually cite at a per sentence or a per clause level which document is feeding the response is becoming fairly easy to do. The last thing that I'll note that I think is really interesting about some of these generative models is that they're increasingly being used as kind of sets of multiple agents or multiple tools, each of which is a particular fine-tuned or guided version of a foundation model. And so this is a screenshot from a startup called Fixie. And each line here, this is Fixie showing its thinking as it's responding to a user request to schedule a meeting. And it's calling a bunch of different agents to figure out things like, when is that person free? What does the user's query actually mean when it says tomorrow? Like, what date is that? And it's literally saying, this is what I'm thinking at each stage. So it's a very different approach to interpretability than some of the more kind of structured data approaches that I showed earlier, like LIME or SHAP. But I think it's highly interpretable to end users. The last thought that I'll share is if you surf the internet for accuracy versus interpretability, you will find charts like this. This is actually from AWS that show a direct trade-off between interpretability and accuracy. And I think this might be true if you literally have like a couple of hours to build a model, release it, and never come back to it. You're never going to improve it. But if you're living in the real world and you're thinking about things for the long term, this is definitely not true. interpretability is actually critical for improving accuracy. It's critical for enabling users, be they external or internal, to provide useful feedback at the specific instance level to researchers and ML engineers. And it's critical for those technical members to dig into bad predictions, understand what went wrong, and refine them and refine the system overall. So to recap, lots of reasons for explainability, most prominently trust, fairness, routing, and the ability to improve systems over the long term. There's lots of types of explainability. We don't have to start with causality. A lot of the time we can get quite far just by sharing what are the inputs, what is the confidence level of the model. When we do dive into causality, local interpretability tends to trump global interpretability. There's a bunch of out-of-the-box, post-hoc explainer solutions for local interpretability, but think about the nature of your problem, thinking about how values are produced in the real world, and if they're not simply linearly additive, then think about how you actually build a model that follows that process rather than slapping on an interpretability layer after the fact. In the long term, explainability always promotes rather than hinders accuracy. Thanks for joining, and happy to take a couple questions.